Hello everyone and welcome to another episode of Noeru Daris. Today we'll be going through physics on fluids. We'll be speaking about various things. We're going to be speaking about pressures. We're going to be speaking about principles. So stay tuned and let's dive deep into it. Alright, shall we get started? So fluids, they are characterized by the ability to flow and conform shape of a container. So what a fluid is, I want you to look at a water bottle and then look at the water in it and see how it takes the shape of the water bottle. So that's a fluid. So how do we calculate density? Density is mass divided volume, and its units are kilograms divided meters. So the weight of the volume, the force gravitational, is equal to density times Vg, or volume gravitational. And this is the weight of the volume. The weight of the volume. Specific gravity is the measure of the density of the substance to the density of the water at 1 atm, 1 atmospheric pressure. So Sg, the formula for it is the density of the substance divided the density of the water. An example of Sg, specific gravity, is for instance benzene, where it has a density of 877 kilograms divided by m3, and then we need to convert. Obviously, we need to convert the water, so it's going to be 1000 kg, the same units. So make sure you watch out for the units. So it's 877 divided 1000 kg, and then it will give you the specific density 0.877. Next we have pressure. So pressure is force divided area. So pressure is force divided area. So how much force you exert on a specific area. Alright, for pressure we have a couple types of pressure. We have atmospheric pressure, so that's in the atmosphere around you, the air. It changes with altitude and impacts boiling of liquids and oxygen affinity in the hemoglobin. So you know how, for instance, atmospheric pressure in Mountain Everest is like you can't breathe there. It's the air is so thin. It's due to atmospheric pressure. Next, we have the absolute pressure. Absolute pressure has to deal with the total pressure that is exerted on an object that is submerged in a fluid. So I want you to imagine this with me. You take a ball and then you submerge the ball in water. Alright, so take in mind that example. There is pressure exerted on the object from the surface, from the liquid itself, and other stuff. So the formula for it is P, pressure, equal the pressure ambient, or the ambient pressure, plus density times gravitational acceleration times the depth of the object. So pressure ambience, or the pressure, or the ambient pressure on surface, plus density, like we said, mass divided volume, times the gravitational acceleration, which is 9.8, and then times the depth of the object. So the PO is usually 1 atmospheric pressure on open days, but depends what the question is gonna give you. It's gonna give you numbers to plug in. Next we have gauge pressure. Gauge pressure uh, it's like the difference between absolute and atmospheric pressure, and it's used in tires or tire checkers. You know, when you go and pump in air in your tire and then you have this meter that checks for the pressure. That's a gauge pressure. And then it has to do more with the atmospheric pressure in the confined space. So the P gauge, or the gauge pressure, is P minus P ATM, or P absolute pressure minus the ATM. So we said the absolute pressure is the ambient pressure plus the density times gravitational times the depth minus the atmospheric pressure. If the gauge is positive, it means it's above atmospheric pressure. If the gauge is negative, it means it's below atmospheric pressure. Next we have hydrostatics. The concept of hydrostatics really deals with the study of fluids at rest, like standing fluids, its pressure, its viscosity, etc., etc. So a lot of stuff. Next we have Pascal's principle. So Pascal's principle here on the right, it's fluids that cannot be reduced through application of pressure. So you know, it's you have the fluid and it can't go anywhere. It can't, like, for instance, I don't know, um, be confined or break down into smaller things. Rather, this fluid is the matter is together. It's like bonded together. It's not easy to break. And then the apply pressure, and the pressure will transmit to every portion of the fluid and the walls. So for instance, I want you to take an example of a hydraulic pressure, or yeah, a hydraulic pressure. You know how, for instance, some hydraulic pressure videos, they're like, they have tons of force exerted on, like, I don't know, a Rubik's cube, for instance, alright? And then boom, it gets destroyed. But in this case, the fluids cannot get reduced. So what happens is that how a hydraulic press really works is that pistons push down, so you have force one. So before I say that, so it's force, the pressure or the power is force 1 divided area 1 equal force 2 divided area 2. So you have force 1 here, so that's pressure exerted on the fluid here, and generates power. So power is generated. So power is F1 divided A1. And then the liquid inside, you see, this is the liquid inside. It's incompressible because of smaller area. So this is a smaller area than this. Alright, so there's a lot of pressure of the liquid against the walls as well. And so it needs to be displaced to the right side. So it's displaced to the right side of the hydraulic lift, and there is a larger area here as well. And power also transfers to the right side of the hydraulic lift, and then power, and then becomes P2. So there is more force exerted here, or more force, sorry, output here, because there is a larger area and it needs more force. So more force output due to the fact that there is a larger area and more power and energy needed. So in order to calculate the output force, it's F2, so equal area, so the area 2, so the area associated with force 2, divided A1 times force 1. Alright, and then F1 is equal F1 times D1 is equal F2 times D2. So that has to do really with just like the distance. And then you got Archimedes principle. Archimedes or Archimedes, I don't know, depends how you say it. I say Archimedes. So it describes the density of the fluid, not the object. Remember with me, density of the fluid, okay? Where the body is immersed in the fluid. You have an object in the fluid and it will be buoyed, or a buoyancy, or flow upwards by force. And force is equal to the weight of the fluid it displays. So have you ever seen sometimes, I don't know, a plastic ball, or you go to the beach, you have a beach ball, and it just like floats? It it's like on the surface. It's not sinking. It's on the surface. You try and sink it, but it's not sinking. All right, and the F buoyancy is equal to the density of the fluid. So density of the fluid, this is the right density symbol, but I don't have it on here, times the fluid displaced times g. G is the acceleration force, don't forget that, is equal to the density of the fluid again times volume of the fluid the volume of the fluid submerged, or the object submerged, times g. So P1 2. So air can be a fluid, and objects are lighter in water than they are in air, and because when you like displace, or like when you submerge something in water, the water the displaced water exerts like force on the object. So there is buoyancy exerted on the object, although there is gravity from the top, but there is also buoyancy exerted on the object, right? That's why you float. Okay, let's say you know, you kneel your head back and then you're looking upwards in the sun and your back is to the water. All right, so that's buoyancy pushing you upwards. Okay, and objects will flow if the average density is less than the average fluid it's immersed in, and the objects will sink if the average density is more than the average fluid it's immersed in. So you see how, for instance, there's this metal block, its density is way more than the average fluid it's in, so that's why it's sinking. All right. But here, for instance, I don't know, I think it's a sponge, but like it's an unabsorbed sponge, so it doesn't even have water in it. It doesn't have that much mass in it, so it's floating. It's floating upwards, okay, because its density is less than the average fluid it's immersed in. Next, we have surface tension. So surface tension causes liquid to form thin but strong layers at liquid surfaces as a result of cohesion. Cohesion is basically the concept of forming like force of attraction between molecules, like hydrogen bonding or van der Waals forces. And cohesion, for instance, an example of that is like when water droplets form on the surface of plants, or you see some insects that like float on the what do you call it, on like bodies of water. That's cohesion. And next you also have adhesion. Adhesion is two or more different molecules bonded together as a result of electrostatic forces. So that's adhesion, two or more different bonds due to electrostatic forces. And then cohesion is hydrogen bonding, a force of attraction between molecules. Okay, and then you have viscosity. Viscosity is the resistance of the fluid to flow. So an increased viscosity increases the viscosity drag, and it's non-conservative force similar to air resistance. So I want you to like imagine this again, or like I don't know if you want to bring an example from the kitchen. I want you to imagine a cup of water and honey or molasses. All right, and I want you to notice that resistance in both fluids. They're both fluids, but one has like low viscosity and the other one has high viscosity. So one has low resistance to flow, and one has a really high resistance to flow. So there is low viscosity fluids like water, gas, and dilute aqueous solutions. They flow easily. Thick fluids like blood, vegetable, oil, honey, molasses, high viscosity, and they flow slower due to the viscosity drag. So the more the viscosity, the harder for fluids to flow, and now you need more energy to be exerted. Next, and it's measured in per second, Pascal per second. Next, you have laminar flow. Laminar flow is basically smooth and orderly flow, and fluid particles flowing in smooth paths in each layers. As you see here, you see they're going smoothly. That's laminar flow. Each layer is moving so smoothly past the adjacent layer. So this layer is going fine, 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 right? But when gravitational force is more than the buoyant force, the objects will sink. Right? Remember last example, there were two forces exerting or being exerted um, on the object, buoyancy and gravity. But if gravitational force is more than the buoyancy force, the object will sink. That's why, for instance, metals sink due to density and due to the gravitational force. So next you have calculated in a pipe or a confined space when like the radius increases, pressure decreases. All right, and when pressure decreases, when pressure increases, when the radius decreases, pressure increases. That is laminar flow, and how you can calculate it in pipes or confined space. So it's the flow rate equal pi r and then to the power 4 times the pressure gradient divided 8 times viscosity times the length. So pi r to the power 4 times the delta P, the pressure gradient, divided 8 times viscosity times length. Alright, next you also have the turbulent flow. This is, by the way, the flow rate is called Poussiel's, some French name, Poussiel's law. right? Next, you have turbulent flow, which is basically a rough and orderly turbulence causing the formation of eddies, swirl of fluids downstream on an object obstructing the flow. So you see here how turbulence or turbulent flow, you see turbulences happening in the ocean as well, and like there is like eddies, which are like swirls of fluids downstream. Turbulence arises in an unobstructed fluid flow when the fluid speed exceeds the critical speed. And in order to calculate the critical speed, this is just here, but if you want to know it or learn it, it's basically critical speed is the dimensionless Reynolds number times viscosity divided density. Density is m divided v times diameter. Next, you have streamlines. What are streamlines? There are indicated pathways followed by a tiny fluid element from one point of flow to another point. It's basically volume V1A1 equal V2A2. So the flow rate is equal volume times area equal volume times area 2. And then lastly, we have Bernoulli's equation. So static pressure in Bernoulli's equation is basically like the absolute pressure. It's almost similar. So it's P plus delta, density, my bad, times gravitational times H. It's almost the same. So H is like elevation. And then you have dynamic pressure, which is half times density times v or velocity to the power of 2. I think v is velocity. Yeah, it's really confusing when you have a lot of v's. And it is defined as the pressure associated with the movement, and it's the dynamic of the fluid. So Bernoulli's equation, what is it really? It states that the total energy of a fluid flowing through a closed system is constant. And its equation is basically this. So it's static pressure P plus half times density times V2, which is velocity to the power of 2, plus density times gravitational acceleration times elevation or height. That's 1. And you can also have, when you have like two parts or two systems, is equal P2, which is pressure 2, plus half times density times velocity 2, plus density times gravitational acceleration times height 2. Alright, it's a really long equation, but in order to just memorize it, just memorize 1/2, and then 1/2 is equal to the other half in order to get numbers. Let's pray that you don't have to find one of the variables and the other half, but practice it as well. So in order to explain this, it's basically the term on the left hand side represents the pressure of the energy of the fluid, while the second term represents the kinetic energy of the fluid due to the velocity. Okay, and the third term represents the potential energy of the fluid due to the height above the reference point. So as the tube narrows, so you see how it narrows here, the speed, the velocity increases at point 2. Thus the pressure exerted on the walls decreases, causing the column to lower the height. DGH stays constant as the cross-sectional decreases, and linear speed increases as dynamic pressure increases and absolute pressure decreases. So here absolute pressure decreases, dynamic pressure increases, point 2. Next, and lastly, we have circulatory system, which is just a closed loop of non-constant flow, low volume lost as it circulates as a result of lymphatic flow, and resistance decreases as cross-section increases. And that's that for today's fluids. I know it's a long video, but hopefully you've benefited from it and you've enjoyed it. This was Mahmoud Nawir. Please like, share, and subscribe, and thank you so much.